Welcome everybody. I'm Enrico Giunchiglia from University of Genova, and I'm going to present my recent work on optimal planning as a constraint optimization, which is a joint work with Professor Taccchella from my university. What we do is start from a deterministic domain with positive cost of transition, and we consider the problem of optimal planning in its full generality. That is, we make no assumption whatsoever about the type of transition and the type of variables that are involved. And we do solve the problem by reducing it to a constraint optimization problem, incorporating a bound n on the length of the plan that we are looking for. And by solving the constraint optimization problem, we can determine whether the plan that we found is optimal, that is, if the solution that we found for the constraint optimization problem corresponds to an optimal plan, or we need to increase the bound n, or it is useless to increase the bound n since the original planning problem has no solution. So our problem substantially generalizes previous work on optimal symbolic deterministic planning, allows to compute non-trivial lower bounds on the cost and on the length of the optimal plans, and produces an encoding which is linear in the size of the original planning problem and the bound n. So this is our formal setting. We start from a finite set of state variables, each variable with a domain, which can be a set of natural numbers, a set of real numbers, whatever you want. A finite set A of Boolean action variables, and indeed we have a copy x prime of x of an x state variables. Then for us, the planning problem is just a triple, corresponding to three formulas. The first formula is I, that corresponds to the initial state, the formula T, which encodes the valid transition, and the formula G, which is the goal formula. Then we have a cost function which is associated to every transition from a state sigma from a state sigma to a state sigma prime because of an action alpha, a cost which is assumed to be positive whenever sigma prime is different from sigma, and which can be positive or equal to 0 when otherwise. And notice that for us, an action is just an arbitrary interpretation of a set of action variables. So for example, if we assume to have a single state variable var and a single action square, then since we have one action variable square, then we have two actions, one action in which we just perform the action of squaring, and the other action in which we perform the action of not squaring. And because of the transition relation formalized as this formula, if we perform the action of squaring, this is possible only if the value of var is positive or equal to 0. And the result is that in the resulting state, var will have its value squared. If we perform the action of not square and in a state in which the value of var is positive or equal to 0, then the value of var will be incremented. And if we are in a state in which the value of var is smaller than 0, then in the resulting state, var will keep its value. Notice that here we have various types of effects. So for instance, we have that var changes its value just by executing not square. Here we have a formula which does not incorporate any action. So this is a substantial generalization on standard planning problem as usually formalized in any classical language. For the cost, we assume that the cost of a transition is equal to the maximum between 1 and the new value and the old value of var. So for instance, given this problem, if we start from a state in which var is smaller than 0, and we want to reach a state in which var is bigger than 0, then there are no solution. If we start from a state in which var equal 1 and we want to reach a state in which var equal 9, then there are infinitely many valid plans, and there are only 3 optimal plans of length 3, 7, and 8. So for instance, in the optimal plan of length 3, we just don't square, and so the resulting state var will be equal 2. When we don't square again, in the resulting state var will be equal 3, and when we square, and so the final in the resulting state var will be equal to 9, which is our goal state. So this is the basic intuition of our our work. So essentially, we start from a planning problem with cost pi c, and when we construct an encoding pi o n and c o n, which, as the notation makes clear, incorporates the bound n, such that if each valid plan of length smaller than n as a corresponding model in our constraint optimization problem with cost, and essentially there is a bijection between the models pi o n and the models of pi o n, the model and the plan of pi of length at most n. While if we consider plan of length bigger than n, then any such plan corresponds to a model of our constraint optimization problem whose cost is guaranteed to be smaller than the real cost of the plan. And these two conditions are enough to ensure that if we find a solution pi o n, if we find an optimal solution pi o n of our constraint optimization problem, which correspond to a plan with at most an action, then pi is an optimal plan. If pi o n corresponds to a model of to a plan of original planning problem with more than an action, then we need to increase the bound. And if pi o n has no solution, meaning that pi o n is unsatisfiable, then this is enough to conclude that our original planning problem has no solution. And indeed, this implies that it is useless to increase the bound n. Indeed, this is not easy to do such an encoding, because here we have a problem which is caused by the generality approach. So the problem is that for each bound n bigger than or equal to 0, this formula just encodes the executable plans of the length exactly n. And as a consequence, if we just append the goal formula at the end of this conjunction to impose that the goal must be true at the step n, then this formula over here encodes the valid plan of a length exactly n, when this is true in general. So the problem that we have is how can we encode the plans that are shorter than the bound, and how to encode plans that are longer than the bound. And indeed, this is a problem, because we know that there are a lot of undecidability results. The most important one in our case, which is a result by Matt Elmer, showing that the plan existence problem in general is undecidable. So how to encode plans that are shorter than the bound? So here the solution is pretty easy, and not surprising, and it's easy. Essentially, it is enough to introduce a no-op action that essentially imposes that when executed, then all the other actions are set to false, and all the state variable keep their value. And also, we have to impose that whenever we execute the no-op action, then the corresponding transition has 0 cost. So this is pretty easy and standard. The problem is how to encode plans that are longer than the bound. So essentially, here we don't have an high-level description of the domain. We just have a transition relation conject normal form. And here the basic idea is to interpret every clause in the transition relation as a precondition of action if the clause does not mention any next state variable, and as a clause which possibly causes some next state variable to change its value otherwise. So in other words, we interpret square implies var bigger than or equal to 0 as a precondition on square, and all the other clauses we interpret them as effect clauses. So as clauses that may cause the value of var to change the resulting state. Then, to every action literal LA, we associate an abstract action variable bar of LA. Essentially, bar of square means that we execute an action in which square was set to true, and bar of negation of square means that we executed an action in which next the negation of square was set to true. Then to every state variable var, we associate a Boolean variable b var, meaning that in the resulting state, the value of var has been possibly affected. So far, what we do now is we do compute the abstract precondition of every abstract state variable of every abstract action, and then we compute the set of next state variable which could be possibly affected by the execution of some abstract action. So for the precondition, essentially we just relax the precondition, saying that it is possible to execute the abstract action square if the original precondition is true, or the abstract version of a state variable has been affected, was true. The negation of square didn't have any precondition in our original transition, so it is always possible to execute the abstract action variable negation of square. For every next state variable x prime, we have to impose that x prime has been affected if and only if some of the abstract action variable has been executed in the previous state. So b var is true if and only if the abstract version of not square is true and the abstract version of its condition were true, or we executed the abstract action square. Indeed, here we have some problem because we see that we have some circularity between the precondition of the action and the effects of the action. So for instance, here b var occurs both in the precondition of the abstract action square and in the distortion effect of the abstract action square. In order to avoid circularities between precondition and effects, we have to impose level ordering constraint, which also allows us to compute a lower bound on reachability of a condition. So for every formula, we are able to compute a lower bound on the number of steps that are necessary in order to make the formula true. Then we have just to relax the goal. So for instance, in our case, the goal var equal Vg becomes that var equal Vg, or the value of var has been affected. So how do we put all the pieces together? So the basic idea of our solution is to build a formula pi on, which imposes that in the initial state formula must be true. In the first step, we have just to follow the standard transition relation extended with an of action. And finally, in the last step, when we allow to have some abstract transition that are imposed by our abstract version of a transition relation. Finally, in the last step, we have a relaxed version of our goal. For the cost of our model is equal to the cost associated to the first end transition plus the cost of performing some action in the abstract version of the transition relation, which is equal to lambda g, which is the level associated to the goal, times the minimum cost associated to the transition. And indeed, if lambda g is equal to 0, this means that the goal has been reached in less than or equal to n action. So what are the results that we are able to reach and to state that we state in the paper? If we start from a planning problem pi c with cost, indeed a plan pi of length k is optimal if and only if there exists a bound n which is bigger than or equal to k, such that pi o n is an optimal model of our constraint minimization problem. For a bound n bigger than or equal to 0, pi o n is unsatisfiable when pi has no valid plan, so it is unsatisfiable. And if we find an optimal model of our constraint minimization problem such that the level associated to the goal is different from 0, when we know that any valid plan of pi has a length greater than or equal to n plus pi o n of lambda g. So n plus the value of lambda g in our optimal solution of the constraint optimization problem. Finally, the size of our encoding is guaranteed to be linear in the size of the original planning problem and the bound n. So this work is a direct extension of our previous work that appeared in GK 2020. It incorporates some idea from the PhD thesis by Nathan Robinson that was published by Robinson, Gratton, Pham and Sattar in pre-K 2010. It reminds some of the reachability analysis that was done back in 2009 by Malta Helmet in his AI paper. While the technique that we use for computing the level associated to every formula is derived from the work by Ilke and Niemela on stable models and differential logic. And here I mentioned also some other paper that appeared for considering lower bounds and computing optimal plans, but all these works just consider classical planning problems. This is everything. I want to thank you for listening, and bye.